Okay, so we'll start with the definition as always. So we define this concept in the context of a general vector space. And remember, every time we speak of a vector space, we think of a quadruple. So linear dependence or independence, that's the quality which applies to a set of vectors, finite set of vectors. I will often denote them with the X letter, all of them in boldface, because all of them, every one of them individually is a vector. Yeah, this will be my set S, which consists of n vectors in my notation. And I will call this set linear dependent. This is the definition goes. I will call this set linear dependent if it's a relatively difficult definition, but the good news is you're probably familiar with it, so it's just a revision. If I can find scalars, as many as vectors, so n scalars, such that these scalars, they meet two conditions or two requirements. First one is that the following expression is positive. You may find this a bit unusual, the way it was given to you. You may saw it in different form, this first condition. Effectively, it means that not every, I'm not sure why it's small, I'll increase this. Effectively, it means that not every coefficient here is zero. This is probably a more familiar statement of this condition. It's more likely, in this form, it is more likely that you remember it, but it's equivalent thing, right? I mean, if you have a bunch of numbers and not everyone is zero, then this expression will be positive. The only condition under which this expression is exactly zero is when every lambda is zero. So it's a very nice mathematical way to say that not every coefficient is zero by saying this. It's a nice trick. If you don't like it, you can stick with this plain English description of this condition or requirement. And the second requirement, which is still part of the definition of linear dependence, is that if you take the following expression, you combine all of your vectors together, scaled by these coefficients, the result will be zero vector. If these two conditions are met, so you have this, you manage to produce a set of coefficients such that not everyone is zero and such that this expression is zero, then you can claim that this set is linear dependent. Okay? This is the official and the only definition of linear dependence. Often, to ease the language a little bit, this expression on the left-hand side, it has a name, nice, easy name to say. It's called linear combination. I use it often, so to ensure you're not confused, if I say linear combination of vectors, I'm referring to an expression like this, because this is a typical linear combination of n vectors. It's when you sum the vectors, when you scale the vectors and then sum them up. Such an expression, often called, I do it very often, on subconscious level, so to make sure you're not confused, this is what I call linear combination of vectors. So this is what we mean, and this is what I mean when I say linear dependence, or when I say system of vectors is linear dependent. There's a opposite definition. Set is linearly or linear independent. Linear independent when you cannot make this happen, or effectively when you cannot make this happen. So when you're unable to produce these n coefficients such that not everyone is zero and such that the corresponding linear combination is zero. That's effectively what we mean when we say set is linearly independent. There's a positive version which often looks like this. Set is linearly independent if the only assumption that linear combination is zero implies immediately that all of the coefficients are 0. It's a big claim because you somehow from one identity produce n identities. It's a lot of constraints encoded in this one, but that's exactly what's the logical, this is exactly the logical opposite of these two conditions.